Hello everyone, I would like to introduce our previous work, which aims to recognize emotion in dialogues. Here is outline of this presentation. Firstly, in introduction, we will describe the background, motivation, and the goal of our work. Secondly, in the part of related work, we will list some related works that focus on the task. In the part of our approach, we will introduce our improving method detailedly. Then the last two parts is our experiments and conclusions. With the development of human-machine interaction applications, textual dialogue scenes appear more frequently. These scenes request effective and high-performance emotion recognition systems. Therefore, emotion recognition in dialogues is getting growing attention from both academic and business community. And different from non-conversation scenes, this task poses a more complicated challenge of modeling context-sensitive dependencies. Most of existing approaches adopt a convolution neural network followed by a max pooling layer to obtain utterance representations. The process proceeds without the guidance of the target utterance. These generated historical utterance representations are indistinguishable toward different target utterance. Emotion recognition may fall in cases where historical utterances express various emotions toward various targets, which may confuse the emotion recognition of target utterances as the figure shows. Motivated by this, our goal is to generate target-specific historical utterance representations conditioned on the content of target utterances. There exists some work aims to solve the problem of emotion recognition in dialogues. Primitive approaches deal with the task as a simply solely sentence emotion recognition task with no consideration of the historical information. To exploit textual information, some work use recurrent neural network architecture, conversational memory networks, attention mechanism, or graph neural network. Besides, some work propose to keep track of states of individual speakers throughout the dialogue. And some of these works consider the context following the target. However, this condition is quite incompatible with some critical situations like real-time dialogue systems in which we possess no future utterances while handling the target utterance. So in our paper, we only focus on the setting that only historical utterances can be utilized. The FERNet consists of 4 successive modules: feature extraction module, attention module, reasoning module, and output module. Figure 2 presents the overall architecture of the proposed model. In feature extraction module, we use two multi-layer bidirectional gated recurrent unit networks to accumulate contextual information from 2 directions for each word of target utterances and historical utterances separately. The inputs consist of 300-dimensional pre-trained glow vectors. The case contextual word is generated by concatenating the hidden states of the case timestamps of forward and backward GRU, where L is the number of layers. We utilize multi-head attention to focus on more relevant parts of each historical utterances according to the target utterances. We also employ residual connection followed by layer normalization to make model training easier. The target-specific representations of historical utterances are obtained by these equations. The reasoning module takes target-specific historical utterance representations and target utterance representations are as inputs. Target utterance representations are updated through time and layers. Each unit in this module takes two inputs, R and Xi. ZT is the update gate. RT is a reset function. RT is the updated representation after observing the T's historical utterance. Specifically, ZT mirrors the relevance between the target utterance representation and the T's historical utterance representation for fine-controlled gating. Compared with global attention computed over all historical utterances, the gate can be considered as local attention, which models short-term sequential dependency. RT is a reset function to determine how much previous information should be ignored by resetting the candidate of update representation of target utterance. As shown in previous works, multi-hop can perform reasoning over multiple facts more effectively, so we stack several layers with outputs of the current layer used as inputs to the next layer. Besides, to model more abundant information, we compute RT in both forward and backward directions and add them together to get RTL as update representation of the T's unit in else layer. In the output module, to preserve original semantic content, we concatenate the update representation and the original representation together. We use a fully connected layer with softmax as activation to calculate emotion class probabilities. We perform experiments on two benchmarks, IEMOCAP and AVEC. They are multimodal datasets involved in two-way dynamic conversations. In this paper, we only focus on using textual modality to recognize the emotion. We use accuracy F1 score and weighted average F1 score as evolution matrix for IEMO dataset. Mean absolute error and Pearson correlation coefficient are used as matrix for AVEC dataset. We compare the FERNet with the following existing approaches: CNN, CLSTM, CFTM with attention, memory network, CMN, dialogue, RNN. The overall results of our experiments are shown in table. We can see that our model outperforms baselines significantly on all evolution metrics of both datasets. Specifically, our model surpasses dialogue RNN by 1.69% on weighted average F1 score. For AVEC dataset, our model lowers mean absolute error by 0.03, 0.027, 0.009, and 0.31 for valence, arousal, experience, and power. Separately, we attribute the enhancement to the fundamental improvement of FERNet, which are generating target-specific representation of historical utterances and handling both short-term and long-term sequential dependencies. In order to demonstrate the effect of each module, we perform ablation studies. We compare the attention-based model with the attention-free model and replace the reasoning model with a memory network. As shown in table, attention module and reasoning module both have a positive impact on model performance. Besides, we perform qualitative visualization of the attention module. The figure shows that for different target utterances, the model allocates different attention towards our historical utterance. It demonstrates the effectiveness of the attention module. At last, we conclude our work in several contributions. Firstly, generate target-specific historical utterances according to the content of the target utterance. Use the attention mechanism. Secondly, we further effectively handle both local and global sequential dependencies to update the original representation of the target utterance to a more informed vector. Lastly, we achieve competitive performance on two benchmarks. Thanks all.